Alright, welcome back. MECH2320. We're working through chapter 32. We're going to talk about synchronous motors. Alright, the whole point of it is, right, where our stator and our rotor are in sync. Alright, that's the whole point behind that. So, let's just talk about them real quick. What are their characteristics? Alright, so synchronous speed. So we just kind of mentioned that. But what that really means, okay, is where the stator, right, has the speed of a certain magnetic field, and the rotor will be able to stay in sync with the speed of that magnetic field. Okay, so what that helps out with is we can operate at a constant speed, very important, from no load to full load. Okay, so constant speed motor, okay, it's able to do that. So it can produce a leading power factor. All right, remember the power factor is the ratio of the real power to the apparent power. Okay, so just a little basic trig function there. All right, and then sometimes, okay, we can operate without load to help correct the power factor. So with this, we have to use the rotor and excite it with a external source of direct current, so separately excited. You guys did some of these labs in the mechanical class when you did the rotating electrical machines lab. Okay, but we have a special kind of squirrel cage type winding on here that's a dampener. Okay, they're the armature windings. Okay, but they're there to dampen the oscillation that happens from the rotation. Okay, so that's really what those windings are there for. They help control, all right, any sort of funky torsional, okay, or rotational type oscillations. Okay, and we've talked about different methods of starting as well. So when we use the armature windings, okay, they help provide a good starting torque, and we can go with low starting current on these. And we can also use electromagnets. Okay, we can use those. Those help lock in the field on the stator. So we can use that. And so when we lock in the field on the stator, the rotor can stay in sync, all right, and the motor's going to run at synchronous speeds for us in that scenario. Okay, there's a couple different ways that we can give that excitation current. Okay, so we can have a separate direct or DC power supply that's connected to it. Okay, we can also have a brushless exciter as well when we go through these. And here's what a picture of one of those might look like. Okay, no brushes or slip rings. The advantage to having the no brushes or slip rings is what? No wear and tear, no mechanical parts or pieces or anything that can cause that motor to go out. So if we take a look at how we separately excite these, okay, you can look at how the DC supply is and how we can control the stator field, okay, where the windings go directly to them. Okay, so very important. There's self-excited, okay, that's where it's starting on itself. Okay, we mount that on the rotor shaft itself, and we don't use an external. It's self-excited when it goes on there. And we did this motor as well when we were in the mechanical labs. Okay, so how do we control that excitation current? Right, we have a, well, you had a dial in your lab when you guys did this, but all right, but we can control the current, and we change the current, changing a variable resistor type scenario. And so we can adjust that current for the excitation piece. Okay, when we're talking excitation, we're talking about getting it to start rotating. Okay, so the advantage of these motors, okay, very good starting torque at low currents. Okay, so we don't have to necessarily worry about a huge inrush of current when we want to start these. They'll start out with a higher torque just because of the way they're they're wound. Okay, so main part of the automatic control for this scenario. The control is going to be based on how we excite it, whether it's self-excited or whether it's separately excited. And you're just going to look through schematics and things like that when we go through it. Okay, so we have DC coils here on the contactors, so just a method of being able to control it there. All right, so we have the two outside contactors, and we use that to disconnect the excitation current to the rotor. Okay, so that's how we do that. And then we have the middle contact that connects and disconnects the field discharge resistor at the correct times. Okay, and we also have a protection piece. All right, we have an out-of-step relay. So this is a different type of timer. Okay, and it's checking for the voltage on the coil. And the whole point that it's looking for is if the rotor's not excited within a certain length of time. All right, so we're sending that field out through the stator. Okay, and if the rotor isn't excited or doesn't get going within a certain amount of time, okay, we drop it out and we'll have to start over with the startup scenario. So it's to protect the stator from drawing too much and damage to the stator. So we use an out-of-step relay that's, it's in line and it's just checking to see if the rotor is actually excited or started up. Okay, we can also use a polarized field relay for this. Okay, what this one's doing is it's sensing the rotor speed. All right, so based on the speed, all right, it can control the contactor, whether the contactor opens and closes. Okay, so the frequency can decrease. I can't speak today, guys. I'm sorry. Decrease. Okay, and so if the frequency decreases, the armature opens back up. So when the frequency increases, the armature closes. So that's how it's detecting, okay, and opening and closing the armature of that contactor, okay? And also, all right, we can use power factor correction, right? Ratio of real power to apparent power. We want everything ideally be operating at 100% unity, okay? That way we are, truly in fact in sync. All right, but the leading power factor, okay, so we can create that by over-exciting the rotor. We don't want a lagging one, but if we get a leading, so remember there's leading and lagging, and then there's normal excitation. We create a leading power factor by producing and over-exciting the rotor. Okay, but what we really want is normal excitation. All right, so the current is sufficient to magnetize the iron core, and we don't need any AC extra current that goes with it, so we can get things rotating. And we'll step into that in some other lectures and some other labs, but just understand that that's really, what we're doing. We want to make sure that our power factor is roughly around 100% or unity when we do that. Okay, and where do we use these type of motor? Where are we going to use a synchronous motor generally? All right, we're talking large horsepower motors for pumps, compressors, centrifuges, and large grinders and things like that. Big horsepower motors, very common in industry as well. All right, well, that's the end of this lecture. This was somewhat review. We talked about these motors in the mechanical class as well, but as usual, email me if you got any questions. Let me know if you need a team meet or Zoom meet or anything else like that. Else, guys, have a great day. We'll talk to you soon. See you in class.